he comes here fairly regularly, I guess, now, and we see him a lot. He always tells us very cool stuff about what's going on in Rochester, and I'm sure he will again today. So thank you.
Great. Thank you very much. It's a pleasure to be here. I'm glad to see some of our students here. I'm hoping I'm seeing some of our future students here, and certainly I hope that you're all excited about optics wherever you wind up. It's great to see the future of the field. So yeah, I'm at the Institute of Optics at the University of Rochester. That's the building, and we're sort of located on the southern shores of Lake Ontario, which is the home to the headwaters of the optics industry. We are completely lousy with companies doing everything from making custom lenses to doing integrated photonics, and it's a great place for people who are interested in the sorts of things that Professor Wyant talked about last night, or that Professor Goodman talked about yesterday during his talk. There's tons of entrepreneurship going on. We have a little local startup company competition called Luminate, and so if any of you are coming out of your undergrad and to reinforce Professor Goodman's message, after you finish your degree, you think about starting a company, come throw an application into Luminate and let us know if you win, because I'll want to talk to you and see what we can do to help you. So within the Institute, we offer ourselves a few degree programs. We have an undergraduate degree in optical engineering and another undergraduate degree in optical science, and to be honest, there's really not much difference between them. And we offer, of course, a PhD program and a master's program that you can get through in a year if you want to do a lot of coursework and not a lot of thesis work, and typically about a year and a half to 2 years if you're interested in a thesis master's. Our graduates from the Institute go all over the place, but as you can see, about a quarter of them wind up in academia, which for an engineering program is a fairly high fraction. A lot of them have wound up here, including our own Professor Wyant, and we're really proud of our alumni. They have gone on to provide what I think is critical to the health of our field, and that is they've gone on to lead at the professional societies that really support our discipline, whether it's the SPIE or the OSA or the APS or these days the ACS. Our graduates go on to leadership positions that make all of our professional careers better. And of course, a fairly large fraction of our graduates go on to national labs and serve the national interests. We, much like the University of Arizona runs their industrial affiliates program, we have an industrial associates program where we bring about 50 companies onto campus twice a year. There's generally a knife fight in the cafeteria to see who's going to get to recruit our students, and I'm very happy to see that. We like our students to have multiple offers and some leverage when they're going out the door. I know that the University of Arizona does the same thing. I bet Montana State does the same thing. It's a great time to be in optics. It's a great community of people to work with. And right now, we kind of command our own price within industry. And it's because what we do is so valuable across so many sectors of the modern world. At the IA, we try to make it edifying for everybody, whether they're to recruit or not. Our students have an opportunity to practice their presentation skills and to practice their interview skills. And then, of course, the real meat of the operation are the interviews, are the internships and jobs that come out of them, networking with your fellow students, and I'm getting ahead of myself a little bit. And of course, the expectations last year for our graduate students went up a bit with the 2018 Nobel, which was awarded in part to Donald Strickland, who I like to point out to our incoming PhD students, did her prize-winning work while a graduate student. So no pressure at all, but we're expecting Nobels from all of you who come to Rochester into the PhD program. And so the subject of my talk, and I'm going to try to stay on schedule, do we have a clock? We have a clock right there. Thank you. Is computed imaging. And I really want to talk to you a little bit about my own work at the end, but mostly I'd like to talk to you about this discipline of computed imaging, whether it's within the context of optics or more broadly several other things, whether it's X-rays or RF. Computed imaging is really at a high point in the discipline right now. How many of you in the audience know what I mean when I say computed, without looking at that, know what I mean when I say computed imaging, or knew before you showed up? You know, I see this a lot. Okay, a few of you, a lot of professors. Okay, I'm glad. Some of you who are professors clearly know, but that's okay. So computed imaging is actually part of the background of the modern world, of medicine, and a number of other manufacturing disciplines. If you noticed last night when Professor Wyatt was talking about founding his company, he was talking about metrology and the measurement of surfaces, and a lot of that has to happen in a computer and winds up being computed imaging, and I'm hoping I'll get to a little bit of that. But computed imaging really goes back even before computers. So I want to talk a little bit about a few foundational technologies in the computed imaging world, and then I'll talk a little bit about my own work. So we're going to start with, over here, something that came out of spin physics, and that is nuclear magnetic resonance spectroscopy, where we explore the local environment in large molecules by probing spin flips with big magnetic fields and radio frequency excitation. And so there were a lot of instruments built to detect the very weak signals coming out of these molecules as the spins would flip over. And it took a little work to understand the physics, and then to develop the techniques to implement the understanding of the physics to create images from the data, but that would eventually become an imaging technology. I'm going to talk to you a little bit about radar, and for those of you who are working in nano-optics especially, I worked in nano-optics for quite a long time. I found that most of my work, I spent time just reinventing things that had been discovered in the microwave community and in radar, but just shrunk down by a factor of 1 million. I'm going to talk to you a little bit about X-rays, a technology that is now 120 plus years old, but that is still very much undergoing a rapid change in development. And who here has heard of optical coherence tomography? Can I see a quick show of hands? Okay, so it's more than I've heard of computed imaging. Great. So I'm going to talk a little bit about my own work in OCT. So if you take all of these technologies, they're built around, first of all, they emerge with the invention, the development of instrumentation that allows us to make measurements that had never been made before. Röntgen discovers X-rays. Really back in the early days, the turn of the century, the turn of the 20th century, a number of people working with fast pulses in electronics discover that they can range their measurements. They can figure out how far away the echoes are coming, and they make measurements that no one's ever made before, and they discover or they develop radar. And NMR, likewise, was built around the development of very powerful magnets and supersensitive radio frequency detectors. And OCT was built around the development of low coherence interferometry, which essentially winds up being an optical version of radar. All of these things, with the application of physics, mathematical physics, and computers, become something much, much more powerful. So I want you to notice a few things. NMR looks like, as far as I'm concerned, a bunch of lines. I don't know what to make of that. My friends in chemistry say, hey, it's a chemical. And I go, okay, that's great, it's a chemical. And this looks like nothing to me, but this is, an old school radar screen. And, you train some kid in the Air Force and the Navy to sit in front of one of these screens, and they go, they're coming, run for cover, get the guns out, whatever it is you do. There's a plane on the way, right? But it takes an expert to understand what that is. And radiologists make a rather nice living interpreting images that look like that. because it takes specialized understanding of both the instrumentation and the subject under investigation and the resultant data set to interpret meaningfully what it means. With a little math and a little physics, we can do better. So NMR, with the application of a bit of understanding of the physics, can be turned into spatially resolved, localized signals that make images that look like that. And that's a very happy patient, because those images were obtained non-destructively of the brain. And that is something that today you don't have to be a specialist to recognize that that's a flight through someone's head that is happening through the magic of the solution of the inverse problem and the subsequent computed imaging modality that results. And of course, we call that MRI today. At this scale, I'm afraid I probably should blow this image up a little more. But radar, that sort of nebulous little blob on the screen that you have to train a specialist to sit in front of and wait to warn you that the planes are coming, turns into something that is recognizable as an image of that's an airfield, actually, because that's synthetic aperture radar system, and that image was computed by taking a radar signal from a plane as it flew over the airfield. But you don't have to have a specialized training to recognize buildings and airstrips and things on the ground. And that's the real power of computed imaging, is that it connects what would otherwise be really difficult data, or at least data that are difficult for the human mind to interpret, unless, like me, you've been raising children to read in the Fourier domain. My kids are turning out a little bit weirder than I thought. But you don't have to be a specialist. You don't have to be able to read in the Fourier domain to understand what that image is, because we've done it with a computer through the magic of the solution of the inverse problem and computed imaging. And of course, X-rays, while we tend to talk about X-ray images, they're not really images, they're shadows. And you take enough of those shadows, and you can, again, solve the inverse problem, do some computed imaging, and produce a cross-section of a patient with an inside view of what's happening with their organs, their bones, without, again, having to do destructive testing, and the patients like it better like that. So, all of these things have a common framework for their development that I'm going to get to. And then the last one, OCT, was something that I turned my own attention to about 15 years ago and started working on how can we make OCT better with the magic of understanding the physics and the power of modern computing. So in the case of X-rays, the transition from X-ray projection, that is the shadows, into computed tomography, CT, happens really through the physics of Beer's law. You have to first be able to understand that when you put a source on one side of your patient, rays, X-rays, travel through that patient and are exponentially attenuated, and that exponent simply contains a line integral through the attenuation constant of your patient. And if you have enough of those views, you can, with a little bit of effort, undo this integral. By making a lot of measurements, you get enough information to undo this integral and to calculate that attenuation coefficient, that alpha. And what you're looking at here is alpha of R. It's the attenuation coefficient of the patient. You might think there are kidneys and livers and vertebrae in there, but you're really just looking at the attenuation coefficient calculated from lots of views of the patient. Similarly, with NMR, you have to add physics. You take Maxwell's equations, the propagation of the radio waves, you add a little bit of spin physics to it, you got to do a little bit of statistical mechanics in here, you calculate Raman frequencies, you add the stat mech, and eventually you get out things like the coherence times and the relaxation times of the spins in the patient. And that spectrogram here is just recording really the signal strength for different components of the spin structure of the thing you're analyzing. You can turn all of that into images with magnetic gradients and phase encoding and things like that by doing this and solving some math and sticking data sets in the computer. And of course, echograms that come from radar, those pings and blips that come out of a radar machine, get turned into images by, again, the common theme here, taking Maxwell's equations, adding a reflectance map into your model for the signal, and then calculating the underlying structure, and the result is called the Stolt mapping. Okay. So OCT sort of fits as a minor player in this pantheon of modalities because it's a fairly raw piece of instrumentation. It's just range finding. I send out a ping, I measure the ping, I figure out how long the ping took to come back, and I plot out the little points just like in a radar, and that's really the state of the art in OCT, or at least it was. But in fact, it's a little more complicated than that. Now, of course, you can't really, it's very difficult to measure the propagation time of light when the propagation scales you're interested in are microns. So we use the next best thing. We use light to measure light, and we do some coherence gating and some low coherence interferometry. But essentially think of this as radar, real coherent radar, not LiDAR, but coherent radar with light. So this is the cartoon of how it works. I take a laser, I shine a laser onto a beam splitter, I keep a local oscillator for part of my beam splitter in a reference arm, I send a bit of the light up into my sample, some cells, a mouse, a zebrafish, the things we like to image, and I bring the whole thing back down to a detector as I move my reference mirror and I sweep out an interferogram that looks like this. And within the OCT community, what's usually done is this envelope is then extracted and plotted as the signal acquired along a line into the sample. The problem with this, and anyone who's already studying optics can tell you, is that light doesn't really propagate the way I've drawn it here. I've drawn the light here propagating along straight lines, along rays, like it's X-ray, right? Like it's X-ray, but I get a signal bounced back at me. And light doesn't really work like that. Light, in fact, propagates in beams, and beams spread. And the beam spreading has the ultimate effect that you have to choose. Would you like to see a big depth of field, or would you like to see a high resolution? And you got to choose. And in the OCT community, when we work in the micron scale of light, the wavelength is around a micron, we find that ultimately we wind up working at resolutions around 50 or 100 microns in order to get a reasonable depth of field. And we just weren't very happy with that. So if you do the same thing for OCT that you do for, say, radar, going from radar echograms to the Stolt map, or for X-rays, going from X-ray projections through the radon transform to computed tomography, if you work your way through the physics and solve, remember I pointed out alpha, the absorption of the patient? Well, if instead we try to solve for the susceptibility of the sample that we're investigating, we discover that there is, again, a very clean mathematical relationship between the data that we collect and the object we'd like to reconstruct. And in CT, we wind up getting something called the projection slice theorem. So anyone who studied a little CT has probably worked out the projection slice theorem and how to invert it. In OCT, we get something very similar, but instead of having data that lie on a polar grid and having to move those over to our Cartesian grid and deal with the nastiness that happens right at the middle in the singularity of the polar coordinate system, we instead have a resampling problem from this grid, which has a much nicer origin. It's hyperbolic. It turns out to actually be an easier problem. So we apply that to data. So here's a typical OCT image. This is a volume image. It's just rendered in a fancy piece of software. But what I want to explain to you is that this image is a phantom. It's just it's a test bed that we use. And it's a piece of rubber, clear rubber, silicone, with tiny particles embedded in it. Little titanium dioxide nanoparticles. They're nice and scattering, so they're bright. They show up well in the signal. And these nanoparticles are all about the size you see down here. They're all around a micron in size. And as you move away from this part of the volume and go up, what you'll see is that they look like they grow. right? And of course, all you're seeing is that optical beams spread, right? And then as you go farther up, they do something even stranger. They don't just grow. They start to get stripy. And in fact, you go up a little farther, and the stripes get even worse, and they become checkerboards. And of course, these are just coherent interference effects. The stripes are the coherent interference of the signal from two neighboring particles. The checkerboards are more than two neighboring particles. So this is a mess. This is a non-usable image if you're doing something like pathology on the cells in your lab, because all of this stuff is fake structure, and that leads to poor diagnosis. So you do the physics, you calculate the relationship between the thing that you're investigating, the susceptibility of the sample, and the signal that you collected, and then you swap that relationship around. You solve the inverse problem. You use that to write an algorithm and do the following bit of computed imaging. That is what results from exactly the same data set. You'll notice there's no spreading, there's no stripiness, there are no checkerboards, there are no false images. In fact, we did the hard work of, in fact, imaging fiducial to make sure that this actually reproduces the thing it's supposed to reproduce. But we've done nothing on the instrumentation side to do this. This is purely an extension of the utility of the instrument through physics, math, and computing to produce something that is significantly more useful. We now have an instrument in OCT that will produce an infinite depth of field at any resolution. So we can go up to the diffraction limit, and we can still give you centimeters of depth of field. So this has had a fairly remarkable effect in what we can do with an instrument. So this is an instrument that we build actually at a company I started with my friend and collaborator Steve Beaupart. And that company produces a handheld microscope that has fixed optics. And the fixed optics are made possible at high resolution because we don't have to move the focus of the instrument in order to gain a view over millimeters of the tissue we're investigating. And it turns out that those are very important scales. We are able to resolve things at around 5 microns while working with 3 microns of tissue depth. Actually, we can go much farther than that, but 3 microns is about where we run out of signal just from attenuation. But what this means is that we now have a very compact instrument that can go in the hand of a surgeon and provide images on the cellular scale. So, for instance, here is just a quick snapshot of unprocessed data from the OCT data set. And this is what happens when you run our algorithm. And I'm not sure if it really pops on this projector. We normally put this on an ultra-high resolution radiologist projector in the surgery. But these are cells. And you can see cell nuclei, you can see cell boundaries, you can see, actually, in the one image, what's called the necrotic boundary of the tissue. And this allows the surgeon then to inspect tissue for disease during surgery. And we've done numerous clinical trials now in breast cancer and in kidney cancer, where it's critically important to know that you've cut out all of the tumor. And all of that's made possible in this handheld wand by computed imaging. So, and this says first conclusions and outlook, and looking at my time, I think these will be my conclusions and outlook. There's another section. So I do other things, and there's other stuff you can do with computed imaging. But computed imaging is really the product of 3 important steps: a brilliant piece of instrumentation, an understanding of the physics underneath it all, and the advent of astonishing computational power. You saw in Professor Goodman's talk yesterday, him talking about 150,000-fold increase in computational speed for the FFT, and all of this happens through FFTs, associated just with computing power. It's even more astonishing than that because we implement all of this stuff on GPUs. And the parallelization of this stuff means that we're not algorithm limited. We do all this imaging in real time at 30 frames a second as fast as we can acquire images. And so instruments, physics, and computational power allow you to do things like replace lenses, obtain infinite depth of focus. This second point is something that in a longer format I like to talk about, but I was really excited about physics when I started out. I started studying optics because I really was excited about physics. I was really excited about sort of, the beautiful mysteries in the universe. As I got older, I got really much more interested in healthcare and in the human condition. And here I had all this training in theoretical physics. What am I going to do with that? Optics is such an enormous opportunity for you because whatever you're interested in, at any point in your career, at any point in your life, optics is going to provide you with a route to address the things you cared about. So I found myself going from fairly esoteric theorems in theoretical physics. It wasn't string theory, but it was almost there. And moving over into a medical device startup company. So as you're thinking about your career in optics, just remember, optics is one of those very special fields. Whatever you care about, there's a path to that thing for you. And lastly, how am I doing on time? I'm out of time, so I'm going to stop there. Thank you very much.
Does anyone have any questions? So if no one has any, I have one brief question. I can
Okay.
ask you. What you were showing at the end, is there a requirement that your OCT data be relatively sparse in order for that to work?
No, that's a good question because, of course, I showed you a thing with a bunch of points. Yeah. And so you might wonder, did he do some funny business with a bunch of points? But like the images of the cells, we have continuous objects and things like that. The only thing that's really built in here that's a bit of a cheat, and actually we have ways around this, but is Born approximation. It's built into the forward model. So it has to be fairly weak scattering, but it turns out that when you're propagating through fat and things like that, the scattering is fairly weak, actually. So it turns out that OCT only works when the scattering is weak. People just don't realize that. Regular OCT doesn't work when there's multiple scattering either. So, yeah.
Any other questions? Another question? Yeah.
What is the smallest feasible resolution of those particles?
Diffraction limit. And in fact, we haven't actually done Na equals 1, and we haven't done any immersion microscopy, but I've done Na of 0.9, and then imaged things that are 100 Rayleigh ranges out of the focus.
So is it fair to say that for at 4 or 5 micron, you can really reproduce the refractive index?
Oh, yeah. Yeah, in fact, we do. In the commercial product, we're at 5 micron resolution. And submicron is possible. But it turns out that the physiologically relevant structures are visible at 5 microns. Yeah.
You deal with multiple scatterings.
I don't. I hope it doesn't happen. It just breaks everything. No, we've done some iterative unwrapping. I've done various variations on onion peeling and things like that. They all get you a little bit further, but the OCT itself is corrupted by multiple scattering, and so we can do a little better, but we started going down that road, and the cost is high and the reward is low.
Do you know Yoav Shechner in Israel?
I know the name.
Some people here know him really well. But when I was visiting him last spring, he was showing me some things he was really excited about. And I don't remember if it was OCT, but it was something like this. And he was showing me how they were going after the multiply scattered, I'll call them photons.
Yeah.
Because I don't remember what wavelength he was at, and able to greatly increase the capabilities of what could be done.
I think, and
I remember it more deeply.
I can't swear to it, but I think he's doing coherent nonlinear optics, and he's looking at things like 3 and 4 photon, and then gating out the others.
In this case.
No?
In this case. This was more just looking at multiple scattering.
Okay.
Specifically saying, I'm not going to assume they try
Tracing back
here,
through.
I'm going to block that. I'm going to go over here and get the multiple scattered photons.
Interesting.
So I can email you.
Love to follow up. Yep.
Cool stuff.
Okay, last question.
I'll be
what is the field of view of your system? And
Yeah.
you said there is no moving optics in it?
Yeah.
Meaning everything
Ah.
is...
There's a little bit of a cheat there. We're scanning the beam with the MEMS device. And our window's about a centimeter by a centimeter. It's actually 0.9 by 9 millimeters by 9 millimeters.
Single frame.
Yeah. But we raster scan.
Sure.
Yeah. But
Your
fixed depth.
frame rate is still very fast.
Yeah, so when I say a frame rate of 30 frames a second, that's a B scan. So that's so that's this way. We take about 30 of those a second. And actually, because this is a 3D algorithm, we actually take a few slices.